All right, so example 7.4 is going to take a look at an energy balance on a turbine. So we're going to have 500 kilograms per hour of steam driving a turbine, and the steam is going to enter at 44 atm, which is a pressure, and 450 degrees Celsius at a linear velocity of 60 meters per second. So we know something about what's happening in the turbine. Then we know that the steam is going to leave the turbine at a point 5 meters below the turbine inlet at atmospheric pressure and a different velocity. We have the turbine delivering shaft work at a rate of 30 kilowatt hours, and a heat loss from the turbine is estimated to be 104 kilocalories per hour. And we want to calculate the specific enthalpy change associated with the process. Okay, so there's a lot of information going on here. We're putting all of our concepts together. So at the end of the day, one of the things that we want to be aware of is what we're solving for. We're looking for specific enthalpy in this case. So we're looking for H hat or a delta H hat in this case. And if we look at the problem, we want to know whether that's a molar specific enthalpy or a mass specific enthalpy. And if we look at what we have in the system, we have things in terms of kilograms. So this is per mass when we take a look at this quantity. So first thing that we do with all of our problems is let's get set up. Let's make sure that everything is labeled so that we're ready to go. So here's a picture that I have drawn of this system to give you a sense of what's going on. So normally when we have a reactor, this is the first thing that's really different. Normally when we've been drawing our reactors, our inlet and our outlet are at the same height. And that's very, very common in some kind of a tank-based system. But this is a turbine, right? If you think of a turbine in a hydroelectric dam, that's big. Water should be falling. So there is a change in height. So that's the first thing that they did. I said, well, the mass flow in is going to be 500 kilograms per hour. The mass flow out is also going to be 500 kilograms per hour if you think about it, because we're conserving mass, but it's dropping 5 meters inside that system. We know something about the pressure, the temperature, and the velocity at the inlet. We know something about the pressure and the velocity at the outlet. We also know that we're losing heat in the system. So I draw that as a dotted line coming out, and I make sure that my heat is negative because that's how we define heat, right? If the system is losing heat, that's negative. Okay. And then we have work, and work is also negative in this particular scenario because work is leaving the system and being done on the environment, and we define that as negative in this class. So make sure you're ready to go. You've got all your numbers where they need to be. And let's start to think about how we solve this system. So the goal is to find H hat out. We know that H dot equals something times H hat. And it could be M or it could be N. We need M dot. So we're going to have to find H dot using an M dot. Okay, so this is just a little reminder to you that we could have an M or an N. It could be flow or not a flow. It's generally a flow in this class. And we just need to be careful about that. So we have M dot. We need to find H dot, and that'll give us the ability to get what we actually want in the system. So let's use our open energy balance for this system. One of the keys to knowing that this is an open energy balance is the fact that we're talking about enthalpy. So when we talk about closed systems, we're talking about internal energy. So one of the keys to solving these problems is going to be to look at whether or not you've got H's or U's going on in your problem. That's one indication to help you figure out if it's open or closed systems. Now, if the system itself is the turbine, mass is crossing the boundaries. And if mass is crossing the boundaries of the system, and the system, let's write this for ourselves, the system is the turbine, then if mass has crossed the boundaries, that's the other indication that it's the open energy balance. Okay, so a couple ways that you can figure this out. So I rearranged this open energy balance so that it's already in terms of H dot. So what that says to me is that I'm going to need to find Q, shaft work, change in potential energy, and change in kinetic. Sorry, I said those backwards. Change in kinetic and change in potential energy. So here's my strategy going forward. I'm going to put all of my M's in terms of kilograms per second so that everything is in the same units. So kilowatts is, remember, this is kilojoules per second. So I'm going to put everything in terms of seconds so that I'm ready to go with my units, and my velocity in terms of seconds is given as well. So that's an indication I need to watch my units. The next thing that I'm going to do is find the other terms in the energy balance using the given information. Then I'm going to solve the open energy balance for delta H dot. And then I'm going to use what we talked about above. All right, so let's solve. So first thing that we want to do is we want to change that mass from a mass flow in kilograms per hour to kilograms per second. So all we're going to do is a unit conversion right there to get 0.139 kilograms per second. This is one of the easiest mistakes to make on a final exam, is not watching your units. So double check. At this point in the semester and this point in your engineering career, hopefully units are not a big deal, but you want to be able to check those really, really fast. All right. Then we also know that work shaft is negative 70 kilowatt hours, which is the same as a kilojoule per second. So we just checked our units there. And then we've got heat, but heat was given to us. Let me move up a little bit. There we go. Heat was given to us in kilocalories per hour. That's not useful to us. So let's change kilocalories into joules. Let's turn hours into seconds. We know 1 kilowatt is equal to 1,000 watts. So our heat is going to be negative 11.6 kilowatt hours. And that's just going to make it easier for us to deal with all of our terms once they're in the same units. Moving on, let's do our, kinetic. Keeps messing those up today. So one thing here that I want to point out is when we do 1/2 mv squared, V itself is being squared. The quantity is not being squared. And this is one of the most common mistakes that I see, is some students square the difference between the velocities. Each velocity is squared and then you take the difference. That's how mathematically that would work. So just keep this in mind as you do your kinetic, especially if it's a change in kinetic. All right, let's move on. So let's put 1/2. There's our m in terms of kilograms per second. Our first velocity is 360 meters per second, so we square that. Our second velocity is 60 meters per second, we square that. And then the difference between those is what we actually want. So that's going to give us 8,750 joules per second. And we know 1 kilowatt hour is the same as a kilojoule per second, which means that 1 kilowatt hour equals 1,000 joules per second, which will give us a final kinetic energy of a positive 8.75 kilowatts. All right, we got one more term. Let's solve for the potential energy in the system. And again, it's the change in potential energy. And the only thing that changes is the height in the system. So in this case, we're going to have 0.39 kilojoules per second, 9.81 meters per second squared for G. And then when this particular situation, the problem tells us that we're dropping 5 meters. So if we're dropping 5 meters, the problem has already defined for us that moving down must be negative. So we technically start at 0 and we lose 5 meters. So that's why this is negative here. And then I'm adding my conversion to the end. So that's going to give us negative 6.81 times 10 to the negative 3 kilowatt hours for potential energy change. Now we go back to our full open system energy balance. We have Q, shaft work, potential energy, and I keep saying those backwards, changing kinetic energy and changing potential energy. So let's put all those numbers in and find that delta H dot. If we do that, we want to be very, very careful of our signs. So you'll notice here that we have a negative for Q, a negative for W, a minus a positive 8.75, and a minus a negative 6.81 times 10 to the negative 3, which turns it into positive here. So the change in enthalpy is actually a decrease of 90.3 kilowatt hours, right? And so this is a decrease because it's a change. So your delta terms can be negative. That's okay for us. All right. All right, let's finish by finding H hat instead of H dot. Remember that delta H dot is equal to m dot times delta H hat. So it could be the change in these specific enthalpies if we had one or the other. So if we rearrange, change in H with the hat over it is equal to the change of H dot divided by m dot. And we're going to take that negative 90.6 kilojoules per second divided by 0.39 kilograms per second. And we're going to find that that change in specific enthalpy is negative 650 kilojoules per kilogram. So quite a lot going on in this problem, a lot of steps, right? And this is very similar to something that you could see on your final exam. What you're seeing is A problem that's got changes in just about everything. It's very important to understand the signs and what the system is and what you're looking for, and make sure that you draw a very accurate picture. And then I recommend having a strategy that helped us quite a bit. We want to make sure that we understand whether it's an open system or a closed system. And then we want to do all of those steps that we saw here to find each term within this open energy system balance so that we can ultimately solve for the change in specific enthalpy. So that's how that problem goes. Double check that you understand each of the steps going forward, because each of those steps is going to be really important as you move on in the next couple problems.